Hi everyone. In this presentation, I would like to share our research at the NYSI department and talk about our initial results on our simulations of rainfall and stream flow over Davao City using climate models. In particular, I will present the thesis results of my two students, Ms. Maria Catherine Lagare and Danica A. Loque. I would like to acknowledge also the contribution and guidance of our partners and friends from UP Mindanao, Dr. Joseph Acosta, who was the project leader of PhilLiDAR 1, and of course, the guidance and supports of our experts from Manila Observatory. Thank you very much to our dear Dr. Gemma Tinarisma, and of course, from Dr. Francia Avila and Celine Vicente. In general, the Philippine climate is um, driven by rainfall. So we actually have our own climate type who that is based on the rainfall climatology, and it differs in the different parts of our country. No? We have four climate types. This climate type was actually formulated by Father Coronas, no, who is a Jesuit priest at the Manila Observatory during the time. So for Davao City, for instance, we are under climate type 4, which means we experience rainfall all year round. And this rainfall climatology is driven by large-scale systems such as the Bagat, the Amihan, Easterlies, of course, tropical cyclones, ITZZ, Intertropical Convergence Zone, even El Nino La Nina, and other systems. You know, for Davao City, um, our rainfall climatology is also very dependent on southwest monsoon and local scale systems such as orographic lifting, um, sea breeze, urban heat, even urban heat island effect. Okay? And in the future, according to the IPCC reports, we will experience more intense precipitation events and more um, intense tropical cyclones. Okay, so this will affect basically climate change, or due to global warming, those large scale systems that I've shown you will also be enhanced, or will affect the rainfall climatology distribution over our islands. Okay. How about for Davao City? So this, I'll be showing you studies from Manila Observatory. These are just some of the studies. Okay. So in the future, according to this study, um, Davao City will experience wetter climate. So this is from 2011 to 2040. So we are actually experiencing the effect of climate change. And in the near future, there's a mixed signal. You know, gray gray raindrops means there will be a drier uh, precipitation, while red, you know, means there will be a wetter precipitation. So there's a mixed signal, but still we will experience a wetter climate, in the mid future projections. In terms of intensity, so this refers to millimeters. So this is the intensity. These are light rains, moderate rains, heavy rains, and these are torrential rains. And in the future, they've seen that there will be an increase in moderate rain, and there will be increase in heavy rain, and there will be increase in torrential rain. Of course, the one of the impact of this increase in torrential rains and heavy rain or extreme rainfall is flooding. Okay. So in this study, in this research, um, we use we performed numerical simulations using numerical weather prediction models coupled with hydrological and land surface models to simulate heavy rainfall and stream flow over Davao City. Okay. So basically, we use climate system models. When we say climate system, it means the interactions. We are referring to the interactions of land, atmosphere, um, the hydrosphere, even biosphere. Okay, but in our study, we basically look at the interaction of land, atmosphere, and water. Okay, and we perform dynamical downscaling. Okay, basically to provide better information suitable for local scale, such as the city scale. Okay, so there are actually um, data, no, global data from different institutions, especially those reported in the IPCC reports. But most of those information, climate informations, are coarse in resolution. So we basically do dynamical downscaling. Okay. And our input data are global, and local data sets also from ground stations and satellite data, or a mix of ground station and satellite data. Okay. So this is um, our domain of study. We focus on the Talomo Lipadas watershed because the available data um, for validations, are only within these two river basin. And please note that our data are from remote sensing data, and we obtained it from the Field LiDAR 1 project at the UP Mindanao. Okay. So what we did is, so we want to simulate heavy rainfall and stream flow. What we did is first simulate heavy rainfall using this model, the weather research and forecasting model, after which the output will be used uh, in the WRF-Hydro model and LSM model to simulate stream flow. Okay. And then this research also produced an initial tool, which is a Linux-based tool. We call it numerical weather prediction-based ready assessment flood tool to automate um, flood forecasting. Okay. So in this research, we would like to answer the following research questions. Number one is, how can we optimize a coupled atmosphere land hydrological models over Davao City? Now, models are basically approximate nature, and uh, as such, errors, from these approximations, uncertainties, and the accuracy of these models has to be studied, and usually these models have to be optimized depending on the domain of study. Okay. So to answer these research questions, we performed numerical experiments based on tested best model settings. So there are many experts who've been using these models, and we can start from there. Okay? And then we perform validation using station and remote sensing technology, such as from those from satellites and LiDAR data, to improve the results of these climate system models. So in particular, we want to answer how model parameterizations, resolutions, and input data affect the simulated rainfall over these watersheds. Okay, and to answer this, we conduct dynamical downscaling. So again, the input data are usually 100 kilometers or 200 kilometers or so. So what we do, and as we know, for those resolution, we can only have maybe 2 points, 3 points, or 4 points for the Philippines. What more for Davao City? So we did dynamical downscaling. This is different from statistical downscaling. Dynamical because we use fluid equations, to solve parameters such as rainfall. Okay, so we did this downscaling, and then we perform sensitivity parameterization experiments. Now, these model parameterizations, these are subgrid models, to help the main model um, and get more accurate, uh, let's say, simulated rainfall. So, but again, we need to optimize, no? And we want to look at the sensitivity of the simulated rainfall to these parameterizations. Okay. So we use these tested parameterizations. We call it WRF-1, WRF-2, WRF-3, and WRF-4. So these are the authors, no, of, um, of these best model setups. No? Dr. Cruz and Narisma are from Manila Observatory, as well as Mr. Olegare, Olegara, Olagera, sorry. And then this is from the developer of the WRF model, and are um, uh, these are from, I think, Thai, no? Who studies extreme rainfall. Okay, and these are their best setup. Okay, so we tested those best configurations, and these are the results. Okay, so at 27-kilometer resolution, basically the model were able to capture rainfall patterns. No? In fact, we see some, this is satellite imagery, no? And we can see that the ITCC was somehow simulated by our models. Okay? Even LPA, no? Low pressure area, and also the Habagat. We can see the southwest monsoon area, no? Were intensified. So basically, the model can simulate these large systems. Okay, but then again, our area is very small, Davao City, so we need to dynamically downscale or increase the resolution of our model. Okay, so and we found that rainfall is very sensitive to physics parameterizations as well as input data. We use different input data, and then even the initial time. As we know, um, nature is very nonlinear. So even the initial time, so chaotic. So even changing the initial time of simulations will also result into a different output. Okay, and of course the model resolutions. What we can control here, of course, is the model resolutions. So this is for the 27-kilometer resolution, 9-kilometer, 3 and 1-kilometer resolution. Okay. And so for the best model setup, we found the WRF-1 and WRF-4 at 1-kilometer resolutions, give the best, more realistic rainfall pattern. Okay. However, this is bias, meaning uh, so the difference between the observed and the simulated data. So this one, it's mean a wetter bias, and drier bias. And you can see that WRF-4 actually reduce the wetter bias. Okay? And then another research questions that we tried to answer in this research is how do model parameterizations, resolutions, and input data affect now the stream flow over watershed? So kanina, rainfall, no? Now, how about the stream flow? So basically, this stream flow is very important, because um, it will give us an idea of possible flooding. Okay. To answer these research questions, we investigate different input forcings for WRF-Hydro. So we perform, so basically the main forcing of WRF-Hydro model is the rainfall or initial runoff. And we did use output from the WRF, or rainfall simulations. We also use satellite-based meteorological data as input for the WRF hydro. Okay, but I will just show you the results for the satellite-based input forcings. Okay, so basically, our heavy rainfall is from satellite data, particular from Global Satellite Mapping Precipitation, or GSMAP. Okay, we use this as input to our WRF hydro model, coupled with LSM or land surface model. So basically, we did this one. We use observe rainfall as input to lessen the errors or inaccuracy from our input data. Okay, because stream flow simulation is extremely difficult. Okay, and then of course again, we can use our results, to our numerical weather prediction based ready assessment flood tool, or we call it NRAF. Okay. So this is a sample methodology of what we did, no? So always in models, we need the input. We define the input, and then so we have pre-processing, and then the processing here, and the post-processing involves mapping. So we usually use external software for the mapping. Okay. So these are the results. So first, these bars, you know, at the top are rainfall data, GS map data, and we can see this is over Talomo. This is an event over Talomo. We can see an extreme rainfall event, which corresponds to large, volume of stream flow. Although over Lipadas, there seems to be a time delay, for the this is the rainfall, extreme rainfall, and this is the extreme observed stream flow. So this is observations. The black line is actually the results of our control run, using the default settings of the WRF-Hydro, and this is basically there's a large, very large discrepancy. So to improve results and further understand the climate system, we first optimize the hydrologic inputs. And what are these inputs? So the first input, very important input, of course, is the river routing. So we need to improve the river routing. So these are the settings of the river routing. So our input data are data elevation models, or DEM. And we obtained data from NAMRIA. So from 125 meter, we downscaled this to 25-meter river routing. Okay, so this is a very high resolution, and I will show you the results in a while. Okay, so the blue lines, are the simulated streamlines, while the green one, these are the actual, or the truth, the real streamlines. And as you can see, for a 300-meter routing grid, the model wasn't able to really recreate the actual pattern, river pattern. As we increase the routing grid, dumadami din yung uh, streams, but still, hindi pa rin nakuha. Note that the red dots is actually our observation points. So we increase it more, up to 25-meter routing for both Talomo and Lipadas watershed, and we found a quite reasonable routing. We simulated a reasonable river routing, and in this routing, we got the exact location of the observed data. Note that this is very important because this observed data, this red dot here, will be used to validate our results. So we also performed, so after improving the input data in terms of the routing grids and in terms of rainfall, we also performed sensitivity experiments using the surface runoff parameters of this model. Okay. So okay. So basically, this is the equation used by the models. Okay. So we did experiments with these two parameters. Okay. And basically the infiltration factor and the saturated hydraulic conductivity. And we found that our results is the stream flow generation is very much affected by changes, of this parameter. Okay. Um, so land surface parameters greatly affect stream flow generation through the infiltration excess or the surface runoff. So yung excess sa infiltration, it will become surface runoff, and then it will go eventually to our stream and will affect the stream flow there. Okay, so we found that higher infiltration factor results to lower moisture, soil moisture content, which then resulted to higher infiltration excess, and vice versa. Similarly, for the saturated hydraulic conductivity, um, higher values enhance infiltration excess. However, it results in earlier peaks. So we are still improving, no, our results, and we are doing the sensitivity experiments to also help us find the optimal values, no, for our model settings. But so far, this is what we got, no, for the Talomo River. Higher um, infiltration factor values at zero point 0.5 is needed uh, to amount for greater surface runoff contribution. And at this, for the hydraulic conductivity, we got this number, no? So these are very different from the default uh, parameters, no, in the model. So we have to find these settings, no? Okay. Similar for Lipada stations, no? We have these values, no, as the best uh, best setup, no, that that was able to capture or somehow lessen the bias, from our models. Okay. So in summary, we are still improving our um, our model setups, our model runs, and hopefully it will help in giving improving the results, the product of this Linux-based automated hydrometeorological tool, which is the NDRAF. Okay. We call it NDRAF. Okay, these are sample products of NDRAF, no, on which it was able to capture heavy rainfall during a flooding event over Davao City. So this is very promising. Okay, this is another example. So we have the hourly rainfall and the stream flow events. Okay, so this is I think this is Davao River. Okay. Okay. So in the future, we want to do further tuning of the meteorological and hydrological models to improve the accuracy of the output. Of course, we hope to improve our computational facilities for faster and yeah. So far, yung predictions namin is the computational time is even longer than the predicted time. So we need to really improve, invest in these computational facilities. And hopefully, we can apply NDRAF, our tool for flood forecasting to other cities. And of course, this study is um, happened, because of the help of our developer data, input data, developer of our models, and of course our partners from Manila Observatory and UP Mindanao, and also Pag-asa. That will be all. Thank you.